So, welcome everybody. We're having another instance of Gauge Theory Virtual. We're happy to have Mike Miller-Eismeier tell us about Q3. I'll be quiet and let him do it.
Hi, thanks for having me. I've talked about some of these results in different contexts, often focusing on the topological aspects of the story. Since we're in gauge theory virtual, I thought I'd try and give more emphasis on all of the relevant gauge theory and some of the technical hiccups we hit along the way. So just to go through some context, which I think most of us are familiar with some of. The invariant I'm going to talk about today is a certain analog of Froishov's correction term, or H invariant, for integer homology spheres. This invariant somehow tells us some of the things you can extract from Donaldson's diagonalizability result, helps to obstruct, well, the key property of this invariant and its monopolar Hegardt-Floer analog, the D invariant, and its generalization to rational homology spheres, is monotonicity. And this is where most of our topological applications are coming from somehow. If I have a negative definite cobordism, here with no constraints on the first homology, if I have a negative definite cobordism between two integer homology spheres, then the H invariant cannot decrease as I go from the incoming end to the outgoing end of the cobordism. Because this invariant is also additive, and the preceding property shows immediately that it's a homology cobordism invariant, this gives a nice example of a homomorphism from the homology cobordism group to the integers. On the other hand, the monotonicity property, it tells us something about negative definite cobordisms, but doesn't say anything beyond that level of generality. Just by reversing orientations, you get a similar but reversed inequality for positive definite cobordisms. But for indefinite cobordisms, you get no constraint at all. This quantity can be whatever integer you want it to be, as soon as, say, b plus and b minus are both 1. What I want to talk about is an invariant very much related to this, which comes from a quite similar story. So to say where it's coming from, I'll first make some brief remarks about the H invariant. A modern perspective on Froishov's invariant. Well, any perspective on Froishov's invariant says that it arises from what's called SO3 equivariant instanton theory. with rational coefficients. And a modern perspective might say that, maybe I should say recent perspective, is that it's extracted from the algebraic structure of a certain chain complex. This chain complex is a DG module over the exterior algebra on one generator. And this invariant sum, it has a special generator associated to the trivial connection. And Froissov's invariant measures interaction of irreducibles with this reducible connection. I'll talk a little bit more, I'll review a little bit more later about how you can extract this from the algebra. But the crucial point I want to make now is that that exterior algebra is coming from the fact that I'm working over, that I'm working SO3 equivariantly. That exterior algebra can be understood as the homology of SO3 with rational coefficients. I have a sort of action on this chain complex of the fundamental class of SO3. And the basic observation that suggests we should, the basic observation here that points us towards another thing we can say is that if I look at the homology of SO3 with F2 coefficients instead, this is still an algebra. SO3 is a group, so I can use the product operation on that group to get a product on these homology groups. And this algebra is now an exterior algebra over two generators, one in degree 1, one in degree 2. So I want to suggest that we'll get somewhere useful by looking at the structure of this, the analog of this tilde complex over F2 with this more complicated algebraic structure. As an aside, if it's interesting or useful, a nice introduction to the algebraic structure I was describing before and how you can extract interesting invariants from it is given in the paper Equivariant Aspects of Instanton Knot Homology by Dehn and Scaduto. Sorry about the aside. Back over here. This is Kim Froissov recently posted a new paper talking about exactly some of the structure you can get out of SO3 equivariant instanton homology over F2. He defines an invariant Q2 of Y, which is an integer associated to integer homology spheres. This invariant satisfies some similar monotonicity results, though you have to be a little bit more careful about the first homology of your cobordism. And if the H invariant comes from the chi3 equivariant homology of this complex, or this complex is a chi3 module in some sense, then this invariant Q2 over here can be extracted from what I'm going to call the chi1 module structure over this complex with F2 coefficients. To explain the numerical discrepancy there, Freyssov's perspective is more in terms of the cohomology of BSO3 generated by W2 and W3, the Stiefel-Whitney classes, which correspond via causal duality to these generators chi1 and chi2. So in some sense, Freyssov's looking at the W2, the contribution of W2 to this complex, which is why the term Q2. Instead of the chi1 module structure, I want to discuss something about the chi2 module structure here. First off, it extends from integer homology spheres to F2 homology spheres as an F2 homology cobordism invariant. It negates under orientation reversal. And while we don't actually expect it to be additive in general, due to some difficulties with the connected sum theorem over F2, at least it increases by 1 every time I connect sum with the Poincare sphere. So I can get examples with Q3, an arbitrary integer. Finally, the most interesting property here is that if we have a cobordism between F2 homology spheres, so that the first homology of W has no two torsion. Another way of thinking of this is by surgery, I can replace this with a cobordism whose first F2 homology is 0. Then we have an inequality bounding the absolute difference of the change in Q3 as I cross the cobordism. It can increase by no more than B minus of the cobordism, and it can decrease by no more than B plus of the cobordism. For B plus or B minus equals 0, we recover the usual monotonicity in the case of definite cobordisms of the H invariant or the D invariant. But we manage to get something new even in the case of indefinite cobordisms, so long as you have this minor control on the first homology.
So, Mike?
Yeah.
So you meant to have absolute values around that, the middle term?
No, I did not. Sorry. I
Okay,
mean,
you'd said
that,
absolute, so I was not sure what you meant.
yeah, sorry. I just mean that because I have constants on both sides,
Oh,
we do get an absolute value bound, just a weaker one. The
yeah,
statement here is
okay,
stronger than what I meant by that.
got it.
So in particular, the absolute difference is no larger than B2, is what I was thinking of.
Okay.
Thanks for asking me to clarify. As a quick remark about a topological application, but again, I'm mostly going to focus on the gauge theory here. If we apply this to the cobordism given by the trace of a surgery diagram for Y, this does give us that the absolute value of Q3 is a lower bound for the surgery number of Y, the least number of components. In a surgery presentation for Y. If you're a little bit careful with slam dunk procedures to turn a rational surgery presentation into an integer surgery presentation, you see that in fact, the absolute value of Q3 gives a lower bound on the Dehn surgery number, or the rational surgery number, I should say. What I want to spend my time today talking about is, first off, I'm saying this is extracted from a certain complex. I want to say what that is. Try and communicate that to some degree. Secondly, I want to try and communicate what Q3 is, how we extract this integer from that complex, what the analogy is to this perspective I was mentioning on the H invariant. And lastly, I want to describe the circle of ideas that goes into proving that inequality in a little more depth than I have otherwise in other places. So to start, let me talk about this complex C tilde. This comes from considering moduli spaces of framed ASD connections. To start a little earlier, if I have an F2 homology sphere, we can partition the set of conjugacy classes of flat connections into those of three different types. There's the trivial connection with trivial holonomy. And because I'm going to be working in a bit SO3 equivariantly, I should say that SO3 is coming from the conjugation action on the representation variety, if you like, or the conjugation action on the framed representation variety. The orbit type of the trivial connection under conjugation is just a point. We have the abelian connections, whose holonomy is contained in some circle subgroup. And their orbit type is S2. I find that there's a two-sphere of abelian connections in the framed representation variety whenever I have a single abelian connection with non-trivial holonomy. And lastly, we have the ones that we're most used to thinking about in instanton Floer homology, the irreducible connections, whose holonomy is not contained in any circle subgroup. There, my orbit type ends up being SO3, arising from SU2 mod at center. I'm going to abuse notation a little bit and say alpha, both to refer to a conjugacy class of flat connection and to refer to its orbit type under conjugation. Using these as our limits, we can define moduli spaces of framed ASD connections on Y. Let's write those as pairs A comma G. A is an ASD connection on the cylinder. G is an element of SU2, which I think of as living at 0 cross a base point in the cylinder. A limits to alpha and beta, respectively, on the two ends. And maybe I'll slide this over so I have a tiny bit more room. Lastly, I want to demand that the holonomy of the parallel transport of G as I take it from 0 to minus infinity is 1. In other words, I'm looking at the space of framed ASD connections where I at minus infinity. If alpha has some addition, if alpha is not irreducible, this space will retain an additional action because this condition becomes weaker. It means less. So just to be clear, this holonomy lies in that orbit, alpha. If alpha is a point, this condition is trivial. If alpha is one of these abelian connections, so its orbit type is a two-sphere, this condition is sort of one dimension weaker than the condition for an irreducible alpha. And what that means is that these moduli spaces retain some of that group action from the conjugation action. Alpha is central. There's an SO3 action on this. Alpha is abelian. There's maybe I should call that SO2. There's an SO2 action on this. And if alpha is irreducible, it's just a space. There's no remaining action whatsoever. And the last bit of data I want to mention is that I fixed the holonomy at minus infinity, but I can still take parallel transport to plus infinity. That gives me a map from this space to that orbit of framed flat connections, beta. Beta is an SO3 orbit, so it retains an SO3 action. I don't know what's going on there. Great. And this map is equivariant under whichever one of those group actions this space retains. What I want to say is, well, I'll maybe skip down the page and then add the comment above in a second. What I want to say is that the complex C tilde is given by taking the sum over all orbits alpha of the cellular chain complex of alpha with F2 coefficients. SO3 has a nice cellular chain complex with 4 generators. S2 has a nice complex with 2 generators. The point has a very simple complex with 1 generator. And these naturally are modules over the cellular DG algebra associated to SO3. In the cell structure I have in mind, multiplication is a cellular map. So the cellular chain complex retains a multiplication, a product operation. So if I decompose this into the orbit types, I have an F associated to the trivial connection theta. I have a lambda of chi2 associated to each abelian alpha. And I have lambda chi1, chi2 associated to every irreducible beta. What I want to say about the differential, because in this case, fortunately, all of these cellular chain complexes have trivial differential. My differential should come from some sort of stronger, maybe a more intricate version of counting instantons on these moduli spaces of flat connections. What I want to say is that with respect to the stratification by boundary strata of this moduli space, I want to say that this map is cellular. In that case, this being a manifold gives me a fundamental class, a fundamental chain in the cellular complex associated to beta. And what I want to say is that the differential is given by just taking chi multiplied by the cellular fundamental class. That this works okay in the abelian case and in the trivial connection case, that, for instance, this element is annihilated by chi1 if alpha is abelian, or annihilated by both if alpha is trivial, ultimately goes back to this equivariance claim over here. Now, the subtlety here is if I hand you a map which comes in from some natural space appearing in nature, it's just not a cellular map. We have to prove cellular approximation results for that kind of thing. And here there's some additional difficulties because the boundary of these moduli spaces should break up in an expected way in terms of broken trajectories factoring through other irreducible flat connections. And these holonomy maps should be multiplicative in the appropriate sense. And when we do our cellular approximation results, we need to be careful that this cellular approximation respects that factorization on the boundary, that when you do your cellular approximation, you still have this boundary factorization. So I'll say that in some forthcoming work with Ali Daimi and Chris Caduto, we prove the relevant cellular approximation results. We state and prove the relevant results. Needed to define this complex to ensure that we get a cellular fundamental class and to ensure that it's that these have the appropriate product relations, let's say. The complex we get as a result is a DG module over this exterior algebra and two generators. And the invariant Q3 is going to be defined as a chi2 equivariant analog of this H invariant. To make sense of that, I want to stop for a moment and let's see. Am I pinned here at all? Can I bring my thing to being the main screen?
You are the main screen right now.
Great. Okay. It's not for me, but that's fine. Is this board behind me reasonably visible?
Yeah, not bad.
Okay. In the complex associated with rational coefficients, I have, for the trivial connection, a single generator, and for various irreducible flat connections, two generators, corresponding to lambda chi3, the homology of SO3 with rational coefficients. In this complex, the differential breaks up as a bunch of components. The part going from irreducibles to the trivial connection, we call delta 1. And the part which goes from irreducibles to irreducibles, but goes from the bottom degree part to the top degree part, we call the U map. The H invariant, at least in, you can define it, what do I mean to say here? The definition in this language is slightly different when it's positive and when it's negative. But in the case that it's positive, this H invariant is precisely the longest type of chain that looks like this over here. It's the largest I, so that I can find an element with dx equals 0, d being the degree 0, the degree -1 part of the differential going between irreducibles, such that I hit x with the U map a bunch of times, then I go to the trivial connection. Oh, big error there. And it survives all of those moves. Say this is like a U chain, a chain of U maps so that you survive to the trivial connection in the end. The H invariant is the longest one of those you can make. So in this picture here, my H invariant is at least 3 because I went one U map and another U map, and then I took delta 1, and this triple composite is, say, 1. The analog for homology would have two coefficients has, okay, well, sometimes there's an abelian connection, and I have these irreducible connections contributing these exterior algebras on two generators, which have four elements in total for each of those, four generators in total for each of those. And I look at the map, the component of the map, which in terms of lambda multiplies by chi2, because the differential has degree -1. This map has degree -3, so I'll call it U3. Actually, for equivariance reasons, there will be, a version of this on the bottom degree parts and also on higher degree parts. I could go from irreducible over to one of the abelian connections. Let's call this D3, and then finally down to the trivial connection. Just as h of y in some sense counts the longest chain of U maps followed by this delta 1 over to the trivial connection, we're now counting the longest chain of these U3 maps, or this V3 map, when I go from irreducibles over to an abelian reducible. I'll see if I can share my screen on this iPad again. So just to put in words what I was trying to talk through. Just as H looks for long U chains and counts how many of those it can find, Q3 looks for long U3 chains and sees how long a chain it can find. Now, just as with stuff involving the H invariant, if I have a cobordism, and I'm going to say I'm going to add a technical condition here. A cobordism is unobstructed if all reducible AFST connections have essentially non-negative index, except for a correction term coming from how reducible those connections are. And this condition I should add is a cohomological condition, essentially. Then I get a chain map. I get an equivariant chain map, in fact. Say W star from C tilde Y to C tilde Y prime. With which sends theta to theta prime, essentially. Theta to theta prime plus some junk in degrees we don't care about. An unobstructed cobordism is necessarily negative definite. It has B plus equals 0. So this implies that, the algebraic structure of these complexes, the definition of these chains and how an equivariant chain map interacts with those, this statement implies that if I have a negative definite cobordism, oh, sorry, I should add a condition here. It multiplies by the order of the first homology. So let's assume the first homology is finite for ease of discussion. When that's odd, when you contain no 2 torsion, this map mod 2 is sends theta to theta prime. And the algebraic structure of these complexes, the definition of this Q3 invariant, then gives very quickly that Q3 of y is less than or equal to Q3 of y prime. But that's maybe not that exciting. That's probably not what you're here for. So let me point out that we can get something more general than this. In an article I wrote with Ali Daimi a couple years ago, we discussed cobordism maps coming from obstructed cobordisms. Our first interest was trying to check that these complexes really are well-defined, independent of perturbation. And the way we do this is we construct cobordism maps for cobordisms which are not unobstructed, but are nearly so. So maybe this index is bigger than or equal to -3 instead of bigger than or equal to -1. The reason we can't work with arbitrary obstructed cobordisms has less to do with the technique and more to do with difficulties involving Uhlenbeck compactness. This prevents us, at least naively, from working with things which are arbitrarily obstructed. But what I do get in this context, maybe I'll say offhand, the way we do this is we do a careful analysis of the boundary components contributed by a neighborhood of these obstructed reducibles. By deleting those, I do get a manifold, a moduli space, which is a manifold, but I get these new boundary components. I need to correct for those in some way. If we apply that method, which there we were focused on obstructed abelian connections. These were the difficulty with checking well-definedness. If we apply this to obstructed central connections, and that means B plus is positive, the results of the method give us the following statement, which is going to at first seem a little bit too weak. I have a cobordism whose first homology of the cobordism and of the boundary with F2 coefficients are all 0. With the condition that B plus of W is at most 2. there is a complex which we call the suspended complex of y prime, suspended b plus times, here 0, 1, or 2 times. This is still a lambda chi1 chi2 module. I can still define the Q3 invariant of this complex, and the Q3 invariant shifts a little bit. The Q3 invariant of this shifted complex is Q3 of y prime plus that b plus term. Now, with this modified complex, we do get a chain map. We don't get a chain map from C tilde y to C tilde y prime, and you shouldn't expect that one exists. But you do get a chain map from C tilde y f2 to a suspended version of C tilde y prime f2. And it satisfies that crucial condition I mentioned earlier. It sends the trivial connection on one side to the trivial connection on the other side, plus some terms that aren't really relevant. And as a result, for cobordisms with B plus at most 2, Q3 of y is bounded above by Q3 of y prime plus b plus, or rearranging, I get half of the inequality I mentioned at the start, and only when b plus is bounded by 2. Now, still restricting B plus and say B minus of our cobordism. The other half of this inequality is given by the fact that Q3 negates under orientation reversal. B plus becomes B minus. And I swap which one is y and which one is y prime. As a result, I get also under similar bounds an upper bound by B minus of W. Now, the case of general B plus and B minus is handled by a silly technical trick. If I have a cobordism with those homological conditions I mentioned, taking a Handel decomposition of that cobordism, just using that Handel decomposition and doing a little linear algebra, this cobordism can be decomposed as a sequence of cobordisms with the same conditions The intermediate things are homology F2 or F2 homology spheres. Each cobordism has H1 with F2 coefficients equal to 0. And lastly, B2 of each cobordism is at most 2. So I take this inequality for each term in the sequence, we add them all up, and we get the desired inequality between Q3 of y prime and Q3 of y. So this is where Q3 comes from, this tilde complex. It is defined by counting these sorts of U3 chains, or looking at how long they are, rather. The proof uses this sort of technical assumption and then a topological trick to handle the general case. I want to make some quick remarks on why that's a little bit unsatisfying, even though we do get the inequality in general, and what might be interesting to look at in future work. Firstly, there is a lot of great and interesting recent work on three manifolds with involutions, getting really neat results, both on just three manifold on knot theory by thinking about double branched covers, about quarks, and I mean about stabilization of quarks. And you might want to try and apply similar techniques as I'm talking about here in that setting. But this decomposition argument is going to make you sad if you try and do that. I don't know how to decompose an equivariant cobordism in such a nice way. In fact, if you told me you can't, I would not be surprised. To resolve that, you should try and improve this construction of ours that handled these nearly unobstructed cobordisms to just handle general obstructed cobordisms. This would already be interesting in the case of just integer homology spheres. Cobordism is H1 is trivial with Z coefficients, so we can get rid of all this homological stuff, but B plus is arbitrary. And that's already quite difficult. Secondly, a technical point I kind of suppressed earlier is that it also matters how many reducible ASD connections are obstructed and obstructions of what type. Here, I'm assuming the trivial connection is the only obstructed connection. None of these abelian connections. But as a cobordism comes to you in nature with, say, 0 or small perturbations, there probably are a lot of obstructed abelian connections. One thing we showed in this paper from a couple years ago is that you can get rid of that problem if you use large perturbations to define your complexes. And that's what we do to handle it here. We use these large perturbations. So I'll phrase that as, because of some technical conditions, involving these obstructed abelian connections, we find it at present necessary to use large perturbations on some of these intermediate three manifolds. Even if y and y prime are integer homology spheres, the intermediate ones over here might not be. And to handle those, I want to use these large perturbations. But just like there's lots of great work with involutions, there's also lots of great work right now with the Chern-Simons filtration. And if you use large perturbations, that goes away. You can't use that. You can't apply this tool to tell you anything about invariance defined using the Chern-Simons filtration. Now, these are both the same issue in some sense. They're both the issue of wanting to handle general obstructed cobordisms and having difficulty doing so because of Uhlenbeck compactness. The second one, I gut feel probably easier to solve than the first one. There might be a trick which lets you shift index in some way without really having to deal with the issue of general obstructed cobordisms. That would be great. But a really satisfying conclusion to all of this we need to have a compactification, even in the case of large B+, which will behave well with the arguments we want to make. The Uhlenbeck compactification is very much not a smooth manifold in large dimensions. The issue being that I keep around this framing, which I lose when I bubble off the base point. So maybe use something like these bubble tree compactifications or something like that. Get a compactification so that this is almost an SO3 manifold. You shouldn't quite expect that, maybe an SO3 orbifold. But if you can find a better compactification and use it in all of these arguments, then maybe you don't need these kinds of tricks. Maybe you can just define the cobordism maps for general obstructed cobordisms. I think we'll stop there. Thanks for your time.
This is really cool stuff. Are there questions? Actually, I'll have you go back to when you did the beta seemed to be a space, not just a connection when you were having alpha and beta. Can you just review that? So is it just the orbit?
It's just the orbit.
Yeah.
So I was being, for the sake of time, I was being a little bit uncautious about the difference there. It's the orbit. Sometimes I want to think of that as a space. Sometimes, like when I'm enumerating these over here, I just want to, I want one for each orbit. And I was trying to be uncareful about the distinction there.
Yeah.
The other thing is that in this condition right here, really that holonomy, I say it's one, which suggests that the parallel transport's like an element of SO3 or something like that. But really, this is an element of that framed orbit of framed flat connections, alpha. If alpha is reducible, that holonomy is not going to be well defined as an element of SO3 as I go to minus infinity. Parallel gauge transformations on the ends will change that holonomy by a factor of U1 in the abelian case or a factor of SU2 in the trivial connection case. So this that's what I was sort of trying to say when I say that this condition says less depending on how reducible alpha is.
Right. And also it looks, we're making the polite assumption that, it all decomposes into irreducible, isolated, non-degenerate, but you have to perturb here, or
Yeah.
perturb, or
Yeah, you absolutely need to perturb. Even if all the things involved, even if your y and y prime are integer homology spheres which don't need a perturbation,
Mhm.
even if everything works nicely up until the end, the moment I do this decomposition argument, I have no control over these things in the middle. So even in the best cases, to get this inequality, you're going to need to perturb somewhere, and probably to use large perturbations.
What flavor perturbations are you using? Is it abstract? Is it
Just holonomic
polynomial?
perturbations. Yeah.
So then are you picking the specific things for the cobordism when you're doing the holonomial perturbations?
Yeah, so the on the cobordism, you do some part on the ends and some part on the compact piece separately to handle the flat connections on the cobordism, which aren't handled by your end perturbations.
Mhm.
But I wouldn't say that we're doing anything novel in particular in the perturbations here. I think that story is pretty old.